A huge thanks to my Patreon supporters for making this episode possible. Good morning, fellow mathematicians! Welcome back to another video. On Monday we talked about a crazy diamond to this, JoJo reference here, and I couldn't stop playing around with those diamonds. So this time it's going to be a two-part thingy. One on Wednesday today and second part on this thing where we solve it explicitly on Friday. I can't stop playing around with those diamonds because they are so amazing. They have such nice properties. They just collapse into something really nice all the time, and the limit as n approaches infinity also exists, and it converges so fast that infinitely many of those diamonds in the sequence added together actually converges too. This is the weirdest stuff ever, and pi pops up yet again when adding those up, and it's just so crazy. I can stop playing around with those. This is why we are going to deal with this diamond today. Once again, we want to generalize it to the nth member basically in a sequence. We are going to turn this into a recurrence relation today, and in the next video we are going to solve this recurrence relation. It's going to be a lot of fun, and this way you can also see how to actually set up a weird sequence like this. It's just like with the nested fractions. It's a really weird sequence you always get out of this, and we are going to dive right in. It's going to be a lot of fun. I hope you are going to enjoy this video. Please watch till the end for the watch time. Really helps out the channel a lot. Also check out Flammy too. Let's dive right into the video. Now, we are going to start off with an easy case yet again. Once again, we are going to talk about summation up until n in some way, but this time we are not summing up n once. We are going to sum up 1 plus 2 plus blah 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 up until n in some way. And we are going to start off with n being equal to 2. Now, we are going to give our sequence a certain name. We are going to call it xn, for example. And the second member is obviously x2 in our case. Now, what is x2 exactly? x2 is basically the summation up until 2 in the diamond, meaning we are going to get rid of all of this and we are going to sum up just 1 over 1 plus 2, big vinculum, main vinculum, over 1 plus 2 over 1. So 1 over 1 plus 2, big vinculum, over 1 plus 2 over 1. And now we are going to actually parameterize this thing a tiny little bit more. We are going to split this up into a sequence in the numerator and one in the denominator. Denominator means down here under the main vinculum, this is the denominator, and the numerator is everything above the main vinculum. Meaning we are going to give this a new name like, I don't know, yn, and down here we are going to have zn. This is how we are going to break it up. Meaning, I'm going to write it out yet again. We are going to define y2 in our case, so later for generalization it's going to be n. This right here is y2 and this is z2, I'm terribly sorry. So y2 in our case is being defined as 1 over 1 plus 2, and z2 in our case is 1 plus 2 over 1. And now we are going to go one step further. We are going to talk about x3. Now what is x3 exactly? x3 is one more layer added to it. So 1 over 1 plus 2 over 1 plus 2 plus 3 over main vinculum 1 plus 2 plus 3 over 1 plus 2 over 1. And now you might notice something curious, namely that y2 pops up yet again and z2 is going to pop up yet again. Meaning we can turn x3 into y2 over 1 plus 2 plus 3 over, and now 1 plus 2 plus 3 over z2. This is curious, right? I mean, we have brought our index back once, okay, one time, but we are still left with a summation of numbers here. But keep something in mind. We are going to define our sequence as follows, namely that this numerator that we are going to have up here is exactly our y3 this time, okay, y with an index 3. And what we have down here in the denominator is, well, z with an index 3. So we can find a connection here between the numerators, namely we are going to make a recurrence relation out of the numerators and out of the denominators. Meaning y3 is thus nothing but y2 over 1 plus 2 plus 3, and our z3 is thus nothing but 1 plus 2 plus 3 over our z2. This is good. We have brought this back somehow. And now we need to manipulate this kind of addition right here in the numerator and the denominator respectively. And there's one thing we're going to make use of here, and that was my initial thought when constructing this diamond, little Gauss namely. Because there's a very nice formula for adding up 1 up until n, namely 1 plus dot 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 up until n. This is just a summation of naturals up until n, and it's going to result in exactly n times n plus 1 over 2. And if you don't know what I'm talking about, link will be down there at the top of the description somewhere. Meaning, if we identify our n in this summation, our n is 3 respectively. Meaning this is going to evaluate to y2 over, and then 3 times 3 plus 1 is going to give us 3 times 4 in our case over 2. And what we are going to have here is 3 times 4 over 2 and the whole thing over z2. Now, that's a complex fraction. We are going to take the reciprocal here, leaving us with 2 times y2 over 3 times 4. And here we are going to have exactly, make a little divider here, we are going to have exactly 3 times 4 over 2 times z2. Okay, this is curious, right? Can we generalize this idea with the numerators and denominators to higher dimensions, up until n, for example? So what is our xn going to look like exactly? Our xn is obviously nothing but, well, yn over zn. But by this observation that we had right here, this is going to evaluate to yn minus 1 over the summation 1 plus blah 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 up until n over, and now 1 plus blah 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 up until n over zn minus 1. This is what we are going to have. Okay, I hope you see the connection, x3, y2 and z2, and this is the same spiel here basically. But now we have found out how we can manipulate this right here. By what we did here, we are going to end up with, on the y2 basically, or the y3 in our case respectively, yes, exactly. So our y3, our yn that we are going to have here in this case, is going to be this manipulated, being nothing but, let me see for a second, 2yn minus 1 over, and now in our case, n times n plus 1. And now the whole thing over, and what we have derived here basically. I was just doing it with numbers so that you can see it better. This is n times n plus 1 over 2 times zn minus 1. So n times n plus 1 over 2 times zn minus 1. And now these are just complex fractions yet again. So taking the reciprocal of this, multiplying this with the reciprocal, is going to give us exactly 2 squared in our case, times n minus 1, z n minus 1 over n squared times n plus 1 squared. Ah, this is good, right? I mean, we have kind of reduced this weird fraction into something really explicit. This is way easier to handle because we are not having this weird fraction anymore. But what is yn minus 1 and zn minus 1 exactly? I mean, if you have a recurrence relation, you want to kind of trace back this variable with respect to n back to this variable once again with respect to n minus 1, for example. So let us take a look at yn minus 1 times zn minus 1. Yn minus 1 times zn minus 1. Now we are going to take a look at what these actually are. If we take a look at their definitions yet again, we can plug some stuff into here. So let us write out what those actually were. So if we had yn, we were rewriting this as 2 times yn minus 1 over n times n plus 1. So we are going to change the index from n to n minus 1, meaning this becomes n minus 2 overall, leaving us with 2 times yn minus 2 over, and now in our case, n minus 1, and n minus 1 plus 1 is just going to be n. And now multiplying this with the new definition for zn minus 1, so making a shift of index from n to n minus 1 overall, is going to give us, down here in the denominator, n minus 1 times n yet again, just like here, and this is going to reduce so nicely, 2 times zn minus 2. And this is so great, right? This is going to cancel out, this is going to cancel out, this and this, leaving us overall with y n minus 2 over z n minus 2. This is crazy because y over z in some way as a discrete variable is going to leave us with x in this argument basically. So x n minus 2. Meaning our xn can be expressed as 2 over n times n plus 1 and the whole thing squared, just bringing the exponent to the outside, times x n minus 2. And this is cool, right? I mean, we have traced it back. We have turned this horrible expression, which goes up until the nth iteration, into a simple recurrence relation that we can solve on Friday's video. And that's going to be quite cool if you ask me, because the solution is pretty nice yet again, and it's going to converge to, yes, some value. And it's pretty cool that those actually converge in the limit as n approaches infinity in some way. And I think that's pretty freaking nice. I hope you enjoyed this video. If you have seconds subscribing on the channel, like, don't forget new snack merch and also engineering clock. Get it as long as it's still available. And up until next video, I wish you guys a wonderful day. Ciao.